Okay, OS Week 2 review. We've done the second week. This is where it starts to actually become hard. Okay, it's not hard yet, but it's where you actually have to do some math. As you saw if you did your section problem sets. So, what did we learn in week 2? We learned about the history of OS and processes and how they're created and controlled. So we're going to start with the beginning with the history of OS. We have 3 main phases, and we'll start with phase 1. Phase 1 is expensive machines and cheap humans. The main important parts about the very beginning of phase 1 is that I/O and computation are serial. With the ENIAC and the plug boards that had to be plugged in to get the different programs onto it, you could not do more than one program on a plug board. And so the CPU was idle a lot because of all the input and output that had to be done for every single program that needed to be executed. After a little while in phase 1, we get to batch processing, which is whenever we get into punch cards and separate machines for input and output. The separate machines are the machines that get like a punch card, then it puts it into a tape. You take the tape into the input of the CPU machine, CPU runs it, puts it on an output tape, then you take that output tape and then put it on the output machine to get your printed out answer that you can easily read. This is a lot faster with input and output than it used to be, even though there is some input and output on the CPU machine itself, which still means that you're going to have some idleness of the CPU. This also means that you can have something running while you're also putting input like onto the input tape, and while you're outputting from the tape to a printer, let's say. So that means that a CPU is getting used a lot more. This is also where multiprogramming comes in, because you could program more than one program onto a punch card, and you could put it on the same tape and it'll run all the programs. The way that it can do this is with interrupts. So let's say that you're waiting for some sort of input from from something out of the OS or the CPU, then it'll run the next program while you're waiting for the input. Interrupts are very important. They're the basis for a lot of things that are very important in this next phase, phase 2. Phase 2, cheap machines, expensive humans. The main thing that we need to know about phase 2 is the interactive time sharing. So there's going to be multiple users on a system now, and that means you're going to have programs that need to be run relatively quickly so that no one user gets put ahead of another one. So the way that we do this is with interactive time sharing, and the way that you interactively time share is with a timer interrupt. So a timer interrupt interrupts a program so that CPU gets sort of evenly distributed amongst the different processes that all the different users are trying to do. So instead of having one program from one user run all the way till it ends and it takes forever, it'll, let's say, take 30 seconds, stop. The next person's program will take 30 seconds, stop, until they all get run all the way through. And then there's phase 3, which is very cheap machines and very expensive humans. This is where things like the personal computer come in, and this is also where a lot of things come in and out of style again. So there were a lot of single-user machines again, so that means people try to get rid of protection, but in getting rid of protection, they realize, oh my god, turns out I still need protection from other processes, not just other users, so they have to re-implement all of that again. There's also like batch processing went out of style after phase 1, but now with supercomputers in phase 3, they're coming back into style. The very main thing that you need to remember is that in phase 3, they're multi-processor computers. So let's say more than one thread on a CPU. So things can truly run in parallel now and not just concurrently. Okay, so next, processes, creation, and control. What is a process? A process is whenever a program is currently being executed. It is also it is also a basic unit of measurement in the OS. It is the most basic abstraction of security, and is created and they are created and managed with system calls. So a note for all of this, during the class we're assuming that we're working with multi-programming, and we have to be able to have interactive time sharing. That's just what we have in this class. That's how a lot of computers are made today. So it's just a good way to remember how to do things. So one thing that's very, very important is the process life cycle. The process life cycle is so important that if you actually look on the rubric for this section on the modules, you will see that it has its own section that you will be able to draw and be able to explain each part of the process life cycle. So I'm going to draw it here for you now. So the different parts of the life cycle. We start with new. So new is whenever a process is first being created. A process is running now, so it is a process, but it's not completely created, so it's just new. It's not ready to run yet. It's waiting for different things to be created for this process to be able to run. Okay, and then we have ready. After everything is ready inside of the new part of the after it's done getting everything ready in the new state, is going to go into the ready state. This means that it has everything that it needs to be able to run on the CPU, and it's just waiting for a time slot so it can run. From ready is running. Like I said, it's waiting for its time slot. Now it has its time slot and it's running on the CPU. Now, from running, you can go back to ready again. This is so important because this is where the interactive time sharing comes in. It was running, but now its time is up, but it still needs to run some more, so it must go to the ready part. Now, blocked. A program can go from running to blocked if it's waiting for input or output from somewhere the OS cannot get it itself. Let's say the system calls wait, and so you're waiting for something to happen that the OS itself can't control. It's going to be blocked. From blocked, it can go to ready. Because after it's done waiting, it's going to go back into the ready state because it can't go right back to the OS because something's being run now. It's already given up its time to something else. And then, so from running is terminated. After it's done running, it doesn't need any more input. It doesn't need any more processing time. It can go into terminated where it's waiting for its parent to reap it. This is the main important parts. You need to be able to know what each of them mean, and you should be able to point out where processes are in this state diagram whenever you're given a description of what's happening. Okay, now back to the slides. The PCB. The PCB is a process control block. The process control block holds the current execution state from the process lifecycle, and it also holds where the address of the process whenever it's not currently running, because the OS doesn't know where it is when it's not in the running state, and so it holds it there for when it is in the running state again. And then the way that we provide a lot of security, because we need it, because we're doing multi-user, we have multiple programs, we need security. The way we provide that is with dual mode execution. Dual mode execution means you have a user mode and a kernel mode. User mode has restricted access, and then kernel mode has unrestricted access to the OS. You're running things in user mode if you're running normal code like A plus B equals C, or anything that's simple that doesn't require anything from the OS other than CPU power, that is. If you're trying to do anything, any of these three different things, okay, if you get an exception, like Norman likes to say, if you try to divide by 0, it's going to go into kernel mode, because then the OS needs to do something with it, because it's an exception, it doesn't know what's happening. An interrupt go into kernel mode, and if you get any system call, or if you try to use any system calls in your code, it's going to go into kernel mode and make sure that your system calls are safe to use. So some important system calls for right now are fork, exec, wait, and kill. These are going to be important for both your project 0 and your questions, I'm sure, that are going to be on the ISP. So fork creates an exact copy of the process that is currently running the fork command. Exec runs a new program inside of that process. So it runs new code inside of that process instead of what was already there. Wait waits for the fork to be finished and is therefore in the blocked state of the program to be reaped. And then kill is for sending any sort of interrupt to any program necessary. So that's a quick overview of everything from this week. I know I stumbled over my words a little bit. Hang in with me. If I forgot anything, please tell me. If I got anything wrong, again, tell me. I'm here to study just as like you are, and just doing it in a different way. Okay, bye.